Okay. Did everybody get a sheet of the listing of the priority groups from top to bottom? Does anybody need one? Because we're gonna be using that as we finish up the naming, which probably will finish up about Wednesday of next week or so. Okay, I resolved the issue of Top Hat and the naming of the alkynes and alkenes. So what I needed to do was I needed to go to the blue book, which is the naming book for organic compounds. And I put this sheet in there, but basically the book is correct because IUPAC has decided to do non-standard things with double and triple bonds. So reading through this, it's like you have to be a lawyer. But first, in terms of this book, the one that's online is not the newest version because they're talking about doing 2-hexene instead of hex 2-ene. And when I tried to look up the newest version, apparently it's only in print and it's like 1,500 pounds or something. Not weight, but by cost. So that's beyond my budget for a naming book. So we know that, Top Hat's using hex 2-ene, 2-hexene. To me, it's like tomatoes and whatever else you can say it. So the key thing is, the rules are the chain is numbered as to give the lowest total possible numbers to double bonds. If there's only one double bond, then you're numbering from the end closest to a double bond. That's essentially how they write this in the book. But when you go to double bonds and triple bonds, what they say is that the unsaturated, unbranched, acyclic hydrocarbons. So let's just unpack those 4 words. Saturated for a hydrocarbon means you have maximum number of hydrogens per carbon. So if I have a 2-carbon alkane, it's CH3CH3, which means it's C2H6. If I put a double bond between those carbons, it's C4. It's C2H4. So single bonds have a C2H6. Double bonds have a C2H4. The C2H6 is maximum number of hydrogens, and so that's called saturated. When you have anything less than that, it's called unsaturated. Right? And you've heard the saturated, unsaturated terms in terms of fats and oils and food and nutrition. It just means that in those saturated fats, it's a long alkane chain, and in an unsaturated, it's got a double bond. So when they say unsaturated, unbranched, they mean double or triple bond, no branching, so a straight chain, acyclic, no ring, hydrocarbon. So what we talked about last time, having both double and triple bonds are named by replacing the ane of the name of the corresponding saturated hydrocarbon with an ending ene. So they automatically say the yne comes last. So it's always an ene. But then instead of them, well, first of all, they gave the triple bond last billing, even though it's lower on the chart. So that's what IUPAC did. I still have issues with IUPAC, but they're not going to listen to me. Numbers as low as possible are given to the double and triple bonds, even though this may at times give yne a lower number than ene. And the way I read that sentence is they're intending that the ene gets the lowest number, but it's really what the book says, whoever is closest to the end. So whatever group, triple or double bond, is closest to the end, that's where we're going to start the numbering scheme. So they give the permission to go from either end. But I think their intent was double bond, but sometimes the YNE will have a lower number. And then when there is a choice in numbering, the double bonds are given the lowest numbers. So in other words, if there's a tiebreaker between triple and double bond, the double bonds are then given the higher priority. Okay, this is going well down levels of naming that I normally would not go. But this is the source. This was the source document before the new one came out that I can't get my hands on. So if you look at this, for instance, here is the simplest one here is to look at the middle one. So we've got a triple bond, we've got a double bond, and so the triple bond is between carbons 1 and 2, the double bond between 3 and 4 because I numbered at the end closest to the triple bond. And so the naming here is still not not the newest version. We would read this as a pent 3-ene 1-ine. So the double bond between carbons 3 and 4 and the triple bond between carbons 1 and 2. So it's IUPAC that's allowing us to have this inconsistency in terms of the ene is higher than the ine on the chart, but yet the ine comes last. Because you get two privileges as you're moving up the chart. You get the numbering scheme biased towards you, and then you get to come last in the list of suffixes. And so for double and triple bonds, they kind of they're kind of wishy-washy on a couple things.
Okay, so, but in the case of the first one, where it's normally starting with the double bond, so if like they're equidistant from the end,
you would give it to the double bond. I don't know that I'm going to draw any problems like that, but the book may have. But I don't know if the book went into this level of detail, like what's the tiebreaker between a double and a triple bond. But the double bond wins. So in this case, that's why they're starting here, number 1 at the double bond and number 6 at the triple bond. So that's the actual language in the blue book. And then there's some other rules here. For instance, what if you can't draw a continuous chain and include all the double or triple bonds? Then there's tiebreakers for that. It just needs to be if you can go in 2 different chains and have the same number of double bonds, it's the longest chain. Otherwise, you're trying to include the maximum number of double or triple bonds in the chain. We're not going to go down that level of detail, but it's here if it's there. So I think I put this in the folder for today. If I didn't, I will after class. If you're curious as to exactly what they have to look at in order to simplify the naming rules, this is the way it's written. So the book is correct. I still disagree, but it's correct. There's nothing I can do about that. So we're numbering from the end closest to either the triple or double bond, whichever one is close. And if there's a tie, double bond gets priority. If there's still a tie, like between 2 double bonds, then it's a question of first encountered substituent. If there's a tie there, alphabetizing the substituents. Okay. So that's where that stands. The book is correct, so the system they use is correct. The YNE comes last. Now for this chart, though, for the priorities for today's kind of naming was halides, ethers, and so for the halides and the ethers, notice that they are second to last on the chart. And what that means is that for the halogens and the alkoxy groups, they have no standing. The only way they influence a numbering scheme is by their alphabetization and if they're the first encountered substituent. So an alkoxy group receives no more consideration than a methyl group. Double and triple bonds have higher priorities. And then when we work to the alcohols are now the top of our list. What they've done is they've broken the functional groups up into oxygens. What are the oxygen? And then thrown in halogens, which I did from the beginning. Okay. So the ones we're working with today, except for OH has a higher priority over everybody so far. And then alkoxies and alkyl groups have like no priorities. Okay, what questions do you have? Number 53. Okay, which one of these compounds corresponds to 2-bromo-4-methylhexene, 3-ol? I don't know. But let's do this. Let's copy that and try and paste it. Blow it up. And let's go through naming the first one, just naming it. And I noticed they did not put E and Z in here, which is good because we're still holding off on E and Z. So how would we name A? Well, I look at this and what I have is I have a double bond and an OH group. So I have two functional groups. So my longest continuous carbon chain has to include the double bond and the carbon attached to the OH, which in this case is a carbon in a double bond. So I've got to find my longest continuous carbon chain. I believe it would be that one. Does that one look like it's the longest chain? Okay, so what substituents do I have? A bromo and a methyl. Because again, end of the line, enough hydrogens to give me 4 bonds. So I've got a bromo and a methyl. What about the OH? The OH is the functional group, the alcohol functional group. So it's not named. It'll be named as OL. Okay. So I've got a double bond and an OH. So I've got a number from the end closest to the OH, because OH is top of those two groups on my list. So that means I need to go 1, 2, 3, 4, 5, and 6, because if I went the other way, 1, 2, 3, 4, the OH would get 4. Now the OH takes precedence over the double bond. In this case, you give the double bond a low number along with the OH, but if it was a battle between the two, OH wins. So it just so happens this one works out that way. Got a 6-carbon chain, which means that I've got a hex. So what would the name of this be? It would be alphabetizing 2-bromo, 4-methyl, hex, dash. The alcohol comes last. It has the highest priority, so it comes last. So I'm going to have a hex 2-ene 3-ol. So that would be 2-bromo, 4-methyl, hex 2-ene 3-ol. Is that what they're looking for? No. That's not what they're looking for. So, correct name for this molecule, not the one they asked about. Okay. So if we came over here and said longest continuous carbon chain that contains the double bond here, the structure is going to pretty much be this. The name is going to be pretty much the same. It's going to be a bromo, methyl, hex, ene, all. So in this case, what's going to be different about the name? The position of the double bond, the position of the OH. So in this case, what's the number on the double bond and what's the number on the OH for the OL? So we've got a number from the end closest to the OH, which means I'm going to number left to right, right to left. Left to right. So I'm going to go 1, 2, 3, because otherwise, if I went 1, 2, 3, 4. So again, having the highest priority on the chart means you take precedence in the numbering scheme. So OH is given precedence over the double bond. And that's why you'll always have that chart to use. If you have that, if I give you, I can give you that, or I will give you that chart to use on exams. Because there's just too much stuff to flat out memorize. There's no learning this, it's just memorization. I'd much rather you put application stuff in here than pure memorization at this point. So that means this is a 4, this is a 5, and this is a 6. So what would the numbering scheme be here? It would be, this would be a hex 5-ene, 3-all, which is actually what they're asking for, right? They're asking for a hex 5-ene, 3-all. But then does the bromo and the methyl make sense? No, this is 2-methyl, 4-bromo. So then we would continue on. Now, we probably could just cut to the chase here and say, I got a name, let's write the structure. So if I do that, then I've got hex. What does hex mean? Hex means I've got a 1, 2, 3, 4, 5, 6 carbon chain. 5-ene means at carbon 5, I've got a double bond. 3-all means at carbon 3, I've got an OH. Where's my methyl group? On carbon 4, and my bromo group is on carbon 2. So it'd have the bromo, then the OH, then the methyl group, with the double bond at the end, and the OH on carbon 3. So if we wanted to go directly to the name, we could go directly to the name, and then I guess we just have to kind of search and see, okay, which one of those matches up. It looks to me like C. Looks like C is the one that matches up.
So for module B, if you were to actually write out the code for that, would you do 4 bromo or first, or would you do
Always alphabetize substituents. So this would be a 4 bromo, 2 methyl hex 5 ene 3. Right, right. So ethers are their own little beasts here to name. So yeah, we need to go over that. Was everybody okay with the one we just did? Now, A would be E or Z. If I wanted to really complete the name, I'd have to add an E or a Z to it, which we'll have to learn how to do. Do I need a cis-trans E or Z on B? Yes? Which one? Cis, trans, or E or Z? For B right here. For this one that we just named. Can I make a friendly amendment? Different groups. Any other opinions? No other opinions? Should we vote on those? If I put in my 2 hydrogens there, then you're exactly correct. Whenever the same 2 groups are attached to one of the 2 carbons in the double bond, it eliminates that double bond from having cis, trans, or EZ isomers. So in this case, the name is perfectly fine. There is no EZ or cis, trans isomers possible. And so that name is okay. For C, whatever its name is, which was the one that they gave before, again, you have a hydrogen and a hydrogen there, so it does not need cis or trans or E or Z. Because whatever this big group is over here, it's cis to a hydrogen and it's trans to a hydrogen. If I move that group down here, it would still be cis to a hydrogen, still be trans to a hydrogen, which means I don't have 2 different stereoisomers formed. Over here, same thing. For this one, there's no cis, no trans, no E, no Z needed. Because again, it has the 2 hydrogens. So I just want to make sure when we can still, cis trans we can do, hopefully not cis trans we can do, EZ we'll be able to do once we get through the other naming. So everybody kind of okay with those names?
What about A?
What about A? So A needs an E or a Z. Why? Because it's got a bromine, a methyl, an OH, and this group, so it has 4 non-hydrogen groups. All it takes to move to E or Z are 3 non-hydrogen groups. So that one has to be described by E or Z. And that one's actually, from the rules I think we talked about on Wednesday, what you do is you compare the atom that's attached to this carbon, the atom that's attached to this carbon, whichever one has the higher atomic number gets the priority. So in this case, bromine versus chlorine wins. Down here it's oxygen versus a carbon, carbon versus oxygen, who wins? Oxygen wins. And so those 2 high priority groups are across or antagon, and so this would actually be the E isomer. But that's the only rule that I mentioned, was the idea of direct atoms that are attached, you're comparing. We haven't gone down the slippery slope of tiebreakers. And it's not slippery, it's a cliff. So once we go down it, we got to go all the way. So that, like I said, let's wait until your head expands a little bit from the rules and then gets back down to its normal size, and then we'll go with those rules, and that way it just won't keep expanding and explode. Because there's a lot of rules, obviously. But hopefully you're kind of seeing some of the similarities. So we okay with this? All right. Question 49. So in question, actually somebody asked about question 49, but so if this doesn't make any sense, you can go to Piazza and listen to this explanation again. Of course, you can listen to it as I record it now again. But so these ethers have their own unique feature. Number one, they are at the bottom of the table. So you would think that they might have a priority higher than a double or a triple bond, but the fact of the matter is they don't. Halogens don't have any priorities, and neither do alkyl groups. And so the question is, what exactly does that mean? And here's what it means. So let me just take this molecule, and how would I name it? Well, number one, as I'm looking through this, I see the ether. So we have to take a step back with the ether, and with the ether, that ether is going to basically become what's called an alkoxy group. The alkoxy group is going to be a substituent to the parent chain. So when we have the oxygen of an ether, on one side is the alkoxy group, on the other side is the parent chain. So we have to make that decision first. Who's going to be the substituent, which group is going to be the substituent, and which group is going to be the parent chain, that then I'm going to take that parent chain and find the longest continuous carbon, number from the end closest to the first substituent, or give priority preference. So that's the first decision I have to make. And that's a decision that's made very simply on the substituent is the group with the least number of carbons, and the parent chain has the most carbons. So if I look at this molecule, I've got 1, 2, 3 carbons, and over here I've got more than 3 carbons. So that means that this group is going to be my substituent, bless you, and this group over here is going to become my parent chain. Now that parent chain has a double bond in it, but that just means I'm going to name and number that parent chain like I would any alkene. So that's the first thing you have to do with ethers, is decide what your substituent is. That substituent is then going to become my alkoxy group. Does that make sense? And once I have that alkoxy group named, it's no better or worse than bromo or methyl or isopropyl. It's just an alkox. It's just like an alkyl group. Is everybody with me? So then my next question is, so for the alkoxy group, it's going to have oxy at the end. And what's going to come before that? The name of the alkyl group that's attached to the O. So what alkyl group is that? It's an isopropyl group, so this is going to become isopropoxy. So that group is an isopropoxy group. So I'm going to adjust my circle here, because that's the alkyl group I'm using for my common name. This is the isopropoxy group with the oxygen in it. So I get rid of the circle. So this is an isopropoxy group. So it's just going to be a substituent. It's isopropoxy and it's based on I. Its alphabetization is based on I. So now I'm going to take this parent chain and just, forget about the fact that it's an isopropoxy group. It's just a group. So now I come over here and I go, oh, I have an alkene. Let's see. First rule, find the longest continuous carbon chain that's got the double bond in it. There's the longest continuous carbon chain that has the double bond in it. And how many carbons is that? 4 or 5. So that's going to make this a pent. So longest continuous carbon chain with the double bond in it. Note that my isopropoxy group I circled, it's by itself. All right, number from the end closest to the double bond. 1, 2, 3, 4, 5. I don't know. Did they change the rules on me again? Yeah, see, I don't believe that's the case. Because in order to get preference in numbering, you have to be higher up on that chart. And so the isopropoxy or alkoxy groups in general, since they're at the bottom of the chart, they get no priority. So I'd have to go through there and read it, but I don't believe that's the case. It's a lot simpler if this is just a group. And I believe that's the case, because it's at the low end. Because here's how I'm going to name it now. I'm going to name this a pent 1-ene. Right? 5 carbon chain, double bond starting at carbon 1. Now what are my substituents? An isopropoxy group and a bromo. Now anybody who wants to say, what about the methyl? It's part of the longest chain. So that's why we have to take this in steps. So the methyl group here is part of the longest chain. If you actually watch that video, you would see that at first I put the methyl group and then I went back, oh no, that's not, that's part of the longest chain, erased it. So I fell into the same trap. So now we have 2 groups, isopropoxy, bromo. That means that what? It's going to be a 2-bromo 4 isopropoxy. 4 isopropoxy pent 1-ene. So again, the alkoxy group plays no role other than maybe it would break a tie in the numbering of the chain because it's alphabetization. But other than that, it exerts no other influence because it's at the bottom, just like a bromo. So that would be its name. And hopefully that's the correct name. So that's how we handle ethers. So it doesn't matter what's in the parent chain. If the parent chain was just an alkane group, I do the same thing. Which side of the oxygen has more carbons? That's the parent, the other one's the substituent. Then take the parent and follow all the same rules as before. That makes sense?
So if the oxygen didn't have isopropoxy, so it was just oxygen, would you just call it
Well, it can't just be an oxygen.
Okay, so you would have to have like an extra, they had more.
It's two choices. It's either an OR group, meaning it's an alkyl group, or it's an OH group. And once it becomes an OH group, it's an alcohol, top of the list so far, and it takes precedence in the numbering scheme.
So, what recognizes the fact that it's an ether based on the oxygen?
The fact that the oxygen is attached to two carbons. So that goes to the idea of what are all the functional groups that we can have, which is a huge table in the book of what are the functional groups. So you have to know that it's an ether. You have to know an ether has an oxygen with two carbons on either side. And that table is this table.
So you want us to memorize that too?
Not everything. Not everything. And first of all, let's take a minute on this table. All right. In red is the actual sort of functional group here. The second column with the classification is what the functional group is. The third one is an example, and then of course because all organic books are organized according to functional group, they all have a different chapter. And some of them you can see are well later into next semester. So don't worry about the chapter, don't necessarily worry about the example. What are these? So when you have a halogen, it's an alkyl halide. When you have a double bond, it's an alkene. When you have a triple bond, it's an alkyne. When you have an OH group attached to a carbon, it's an alcohol. When you have an oxygen attached to two carbons, it's an ether. I wouldn't worry about thiols right now. Thiols and sulfides are not really at the top of my functional group list right at the moment. Aromatics with a benzene ring. What's a benzene ring? It's a 6-membered ring with alternating single and double bonds. Ketone. Carbonyl functional groups. So the carbonyl functional groups are the ones that get to be a little, they're not tricky, it's just that there's a lot of them. So if you're looking at a carbonyl, first of all, this is just the CO double bond by itself, nothing else attached to it, is called a carbonyl group. The same way as an OH group that's not attached to anything is a hydroxy group. So this is a carbonyl group. Typically for our functional groups, you have a carbon group on one side of the CO double bond, and then what's attached to the other side is what dictates what exact functional group you have. So for instance, if you have a C double bond O with an H, that's called an aldehyde. When you have two carbon groups attached to a carbon-carbon double bond, that is called a ketone. No Y in ketone. When you have what else can you have? An oxygen. Well, when you have an oxygen attached, it can be one of two things. That oxygen could have an H on it, at which point it becomes a carboxylic acid. Right? We dealt with carboxylic acids this week. It was one of the functional groups that we were trying to recrystallize. If, on the other hand, your O is now attached to another carbon group, that's called an ester. Functional group. And then the other functional group that I put with precedence is if you have a nitrogen group attached on one of the sides, and that nitrogen could have two H's, one H, one carbon, two carbons, that's called an amide or an amide. And you may have talked about amides in your biology class because amides are what are used to make proteins. Carboxylic acids, when they have, oh, there's one other one. So what happens when you just have a carbon, I'll stay away from the R here. When you just have a carbon attached to a nitrogen, that's called an amine. So when you have a carboxylic acid with a carbon with an amine attached to it, you have a amino carboxylic acid, which is shortened to be an amino acid. So where the things they've included extra in that table, I strip them down to this. This is the bare essentials of carbonyls. So you don't have to worry about carboxylic acid chlorides, anhydrides. We'll get to those next semester. So with those functional groups, yes, it would be very, very, very helpful to know what those are. And you're going to need to, or at least be able to pick them out of the table, because we're going to go through the naming of all these functional groups. Plus, if you go and look at real live organic molecules that have a purpose, not that they all don't, but whoa. That structure is called Taxol. And this is an anti-tumor drug. When I first started teaching 27 years ago, it was in clinical trials for, I believe, ovarian cancer. It's now become used in other treatments of cancer. It has a fun history because it was actually isolated from the bark of the California yew tree that grows in Oregon. So the National Institutes of Health had a program where they encouraged researchers to try and get anti-tumor drugs from natural sources. So everybody was going and getting little sea urchins and pieces of coral. Unfortunately for the sea urchin, you can't get the anti-tumor drug out without it seeing a blender from the inside. So sad sea urchin, but if there was an anti-tumor activity in there, they would then take it, test it. If they found anti-tumor activity, they would have to separate all the compounds until they found the one that gave you the anti-tumor activity. Of course, the ability to kill cancer cells also carries with it maybe the ability to kill healthy cells. So not all drugs that kill cancer cells are good because they also may kill everything. So they went through Taxol's, one of the more famous drugs that came out of that initiative. And so what they did was they got it down to this structure. They had to figure out what it was. I happen to have gone to school. Well, I happen to have gone to graduate school at Duke, and one of the professors there actually solved the structure of Taxol for the drug company, or for whoever was doing that. And so basically they had to grow a little teeny tiny crystal, a perfect crystal, not what you grew in lab this week, a little better than that, but a really teeny tiny, perfectly shaped crystal to pass an X-ray beam through, and then they could get the exact structure of the molecule, including all of what we're going to learn about chiral centers that are in this molecule. So once they determined the structure of it, then they can say, well, okay, can we synthesize this? Because there's not enough bark of California yew trees to get enough of this material to treat all cancers. So then you take a look at this, and then synthetic people say, okay, how am I going to make this? And so then that starts the process of trying to synthesize the drug. which is a lot of drug discovery process. And we're going to have a person come in from Monsanto this sometime in, I think, October or November. I probably am going to have her come in and maybe talk to you about her she was looking at herbicides and fungicides, but the process to develop herbicides and fungicides in agriculture is the same process that's used to develop drugs in the pharma industry. And so if you're ever wondering, like, why am I learning all this stuff? This molecule is like, that's one of the reasons why, because this molecule has a very good purpose in life. Why do I have it on a slide? Well, because look at all the different functional groups that are in this molecule. And we can just pick a few of them out. For instance, here's a carbon-oxygen double bond with a carbon on one side and an OR group, or an O carbon, so it has an ester. Sorry, it has an ester. It has an ester functional group. There's an ester, and I think there's more in there. Like, here's another ester. Here's an alcohol. Here's some benzene rings or aromatic rings. Here is an ether over here, the oxygen attached to two carbons. So I think some of the problems in terms of functional groups, they'll give you a molecule like this and they'll circle them and say, what's the functional group? The thing with carbonyls is they always have a carbon on one side. It's what's on the other side that dictates what they are. So there's an alkene. I think this is a good one because it has almost every functional group. Ketone. So you can go through and pick out the functional groups that are in this molecule. But that's part of the reason why we need to know the functional groups, or at least be able to recognize them, because we're going to name them. Now on that sheet, you basically have them as if you write the structures in on the left-hand column, which I will do on the sheet that you get, and we'll do as we go along. So what do I want you to know? We're developing that list. But as far as carbonyls go, that's the list of carbonyls. Now, if you download this PowerPoint, once I put it up, just realize that when I do a screen capture, I have to blow it up. And when I blow it up, when it comes back to size, this is what it looks like. So you might have to crop it and enlarge it if you want a picture. What else? So the big things are alcohols. The big things are ethers. Alcohols automatically take precedence. This, we haven't done any rings. Just to set up a ring, and so with the rings, just kind of we can go over this on Monday as well. So for rings, there's two situations for cycloalkane rings. One is where all the groups that are attached to the ring are just low priority, no priority groups, like the one on the right. So none of those groups that are attached to that ring have a priority. And if they don't, then we go back to our rules for numbering rings, which says find the lowest total sum of the substituent numbers. So the sum of the substituent numbers is only for rings that have no priority groups attached to them, which would be the one on the right. The one on the left has two priority groups. Number one, the double bond is in the ring, and then the OH is attached to the ring. So whenever you have a group that's part of the ring, like a double, and double bonds are the only things that can be part of rings. If you think about a triple bond being linear, the ring has to be like 7 or 8 carbons big in order to accommodate a linear part, and we're not going that big. So a 6-membered ring with a triple bond isn't going to form until next semester. The double bond then, if it was just a double bond, we would number at either one of the carbons because the double bond has to be carbon 1 in the numbering scheme. The first carbon in the double bond's got to be number 1. The OH overrules the double bond, so in this case, the OH says, I'm carbon 1. Now, am I going to go clockwise or counterclockwise? Now the rule is I'm going to go whatever way to hit the next priority group, and if there is no priority group, then the next group. So in this case, the numbering scheme would look like this. And so this would be a cyclohex, then a number, then an ene, then a number, then an ol. So with rings, and we haven't talked a lot about rings, so maybe, if you have questions on that, put them on Piazza or bring them to class and we can do more of the rings as we go through. They have their numbering systems basically are also based on priority. Okay, your take-home quiz problems, you can put them on the table on your way out.